So this is a review video about section 2.1 and 2.2. First, we're going to focus on tangent and velocity problems. Rate of change is how one quantity changes with respect to another. An example could be cycling with miles per hour, or an example could be degrees of Fahrenheit as you increase altitude up a mountain. So now, how would you find the average rate of change if someone went from standing to sprinting to flying? Let's take a look at an example with Olympic sprinting in the 200-meter. Find the average rate of change on the interval 9:15. Remember, it's a change of distance over time, which is your y over your x-axis. I'll pause the video if you want to try to figure this out. Once you've solved it out, you see that we can get 11.6 meters per second as the average rate of change between the 2 points. Let's try one more example dealing with average rate of change with another Olympic event, possibly a marathon. Let's find the average rate of change on the time interval 1 to 5, dealing with hours and miles here. So go ahead and draw the points and then pause the video if you want to try to do this one on your own. Remember, it's going to be your rise over your run when solving. After you find the initial interval from 1 to 5 hours, go ahead and try these next two as well. Pause the video before the answer comes up. Okay, so anybody who actually solved this problem out, it's got very funky answers here, but this is what it should look like. You got your rise over your run, and it's the same process just for the average rate of change between the 2 points as we just did last time. Just a quick recap on how we get those answers. For the interval 1 to 2, you can see our points are 1, 2, and 2, 6, and so 6 minus 2 is going to be 4, and 2 minus 1 is going to be 1, so 4 miles per hour. The last example was dealing with secant lines, but now you can see a tangent line's been added to f of x. It's supposed to not go through more than once. It's supposed to just touch the tip of the point and never again. Just get as close as possible and touch that point. And that line is going to provide us with slope information. So if we draw a second point on there and use the rise over run technique we already know, we're going to be able to find out the instantaneous rate of change, which is going to be the rate of change at an exact time point. So now look back on the graph, pause the video, and try to solve this problem. So at the time point 1, we see that the instantaneous rate of change is going to be 2, because 4 minus 2 is 2, 2 minus 1 is 1. That's our technique we already know. So now, to find the equation of a tangent line, we're going to plug in the slope we just found and the time point into point-slope form, and this will give you the equation of the tangent line. So here we're looking at the function x cubed. So now we're going to try to estimate the instantaneous rate of change by using different time intervals in the average rate of change. So solve these out and then check your answers. Pause the video real quick. So for this example, you guys should have gotten 5, 3.31, and x cubed minus 1 over x minus 1. Next, you guys need to draw a tangent line at the point 1 and estimate the instantaneous rate of change using the technique we've already seen. On the tangent line, there's the point 0, negative 1.5, and 1, 1. So if you do 2.5 over 1, you're going to get 2.5 for the instantaneous rate of change. Re-looking at the equation you found on the interval 1x, we can make the prediction that as x gets closer to 1, the average rate of change of x cubed minus 1 over x minus 1 is going to approach 3. We can see this because as we're picking numbers that are getting closer and closer to 1, our number is getting smaller and smaller but closer to 3. Now, a way to numerically check if we're correct by saying that it approaches 3 is to plug in values extremely close to 1 into the function that we have, like so. You can see that as x approaches 1 from both sides, that the y value is extremely close to 3. Thus, that is our limit. So as I said, we just found our limit numerically, but there's another way, graphically. You can plug in the x cubed minus 1 over x minus 1 into your calculators and see that as the f of x equation approaches x equals 1, it gets extremely close to 3 on both sides. So try one of these without a graph, just using the interval 2, 4, and your equation f of x equals 8x squared. You would take your point 4, square it, multiply it by 8, 128, and then take 2, square it, times 8 is 32, so 128 minus 32 is 96 over 4 minus 2, which is 2, giving you 48. So using the same technique we already know, if you're given an interval of 2 different x points, plug them into your f of x, and you'll find the rate of change on that time interval. So now we're going to begin with section 2.2, which is talking more about limits and how you find them numerically and graphically. So here's 3 quick problems. I want you to see if you can find these out numerically using a table like I just showed you. So for the first problem, in our calculators we want to plug in 1.9, 1.99, 1.999, etc. and the opposite, 2.001, 2.01, values close to 2. When we do that, we can see from both sides that we're getting close to 1. For number 2, as we plug in units close to 0, we're getting near 2. So we're going to assume that the value of this limit is 2. The last problem, when you plug in numbers close to 0, you can see that it exponentially grows. So we're going to go ahead and take a look at what all 3 of these are going to look like, but graphically. You can see number 1, this is the graph of number 1. It clearly approaches 1 as x approaches 2. For the second problem, as x approaches 0, the limit on the left and the right, even though it is not a determined spot, is approaching 2. Lastly, number 3 is approaching infinity on both left and the right side. Now I know that we said it did not exist on this page, but really the more accurate thing to say is that it is approaching infinity, that the limit approaches infinity. So just a notation reminder, when you're presented with something like this, you would say the limit as x approaches a of f of x equals L. A couple reminders of general rules too include that if L is not a finite number, then the limit does not exist, as well as the left and the right limits have to match. If they do not, then it does not exist. So recapping on an example from a while ago, with a vertical asymptote at 0, the left and the right limits approach infinity. So I know numerically we thought it did not exist because it's exponential, but it's really infinite. So now I'll go ahead and pause the video and try to evaluate these 2 examples numerically. There's one error here. The limit is supposed to approach -3. So as you plug in values extremely close to -3, you're going to get an output of things close to -1. Here's my second mistake. It says 1's the limit of number 1, but it should be -1. As for number 2, as you plug in values extremely close to -2, your output's going to be extremely close to 8. So thus our limits are going to be 1 and 8 respectively. Now for the graph shown, what would the limit be at x equals -3? Since both sides are approaching infinity, the limit would be infinity. Now for our second example, what about as the limit approaches x equals 7? Well, since both are approaching the left and the right at 0, the limit is going to be 0. And you could ignore the point at 7, 3. Try one more here, solve for h of x as x approaches -2. And yes, the limit is going to be 4. Just for anybody who still doesn't grasp the asymptote idea, is that the graph on the left does not have a limit because f of x approaches -infinity from the left, but +infinity from the right. However, the graph on the right does have a limit of infinity because both sides approach the same thing. So now the last 2 examples are going to be piecewise functions, and I'm going to show you different problems, and you're going to have to find the limits based on this. So go ahead and take a picture of it or pause, whatever you want to do, draw it again, but here are the limits I want you to solve for. So the limit of -8 has got an open hole, so it's going to be does not exist. The limit as you approach -4 is going to be does not exist because from the left it's 0, but from the right it's 8. The limit as you approach 0 is going to be 0. The limit as x approaches 2 is 2. The limit as you approach 6 from the left is 2. From the right is 8, and those do not match, so this does not exist at the point 6. The last example of the video is going to be one more handmade piecewise function. Why don't you go ahead and fill this out, and then I'll just show you the answers right after. So for the graph of f of x, as x approaches -6 from the right, you can see the limit is 5. As x approaches -3, it's 0. As the limit approaches 1, it's 2. As x approaches 3, it's infinity. As x approaches 5 from the left, it's 1. And 8 from the left is -infinity. Thank you guys for watching. I hope this helps you study for the final.